So during summing amplifier, that means adder, as you see in this circuit, it has different input signals to the inverting terminal of the op-amp, that we can call it summing inverting amplifier. Sum as inverting amplifier, but add more voltage sources, so more voltage, more input voltage to the inverting amplifier, that we call it summing inverting amplifier. So as you know, I1 plus I2 plus I3 plus IN etc, that's the same as or equal to minus of IF. If you remember in the op-amp circuit or rules, I1 plus IF is equal to 0, so virtually short I1 equal to minus of IF. So let's analyze this circuit, how to get the gain of this op-amp, or how to become this summing amplifier is an adder. As you see, V1 sort of R1 go to the V inverting, the same V2 sort of R2 go to the inverting signal, the same R3 sort of R3 go to the inverting signal, the feedback V out back to the inverting signal. So this is summing inverting amplifier. So let's see analyze by using applying KCL. KCL as you know, I in equal to minus of IF according to op-amp circuit analysis. So we use I1 plus I2 plus I3 equal to of minus IF. So I1 plus I2 plus I3 equal to minus of IF. So when you simplified I1, minus I1 minus V1 minus of V inverting over R1 plus the same I2 minus V2 minus of V inverting over R2 plus when you simplified I3, V3 minus of V inverting over R3 equal to IF. So minus of V out minus V inverting over RF. So our V out enter to the inverting, so minus of V inverting. So as you know, V inverting and V non-inverting are equal according golden rule, virtually ground. So V non-inverting is ground, so V non-inverting becomes 0. So according to the rule, V non-inverting equal to V inverting, so this becomes 0 because non-inverting is grounded. So by this principle, V1 minus 0 over R1 plus V2 minus 0 over R2 plus V3 minus 0 over R3 equal to minus of V out minus 0 over RF. So our result becomes V1 over R1 plus V2 over R2 plus V3 over R3 equal to minus of V out over RF. So this means our V out means when you simplify V out becomes minus RF over R1 multiplied by V1 plus the whole. Let's see, this minus becomes the whole on the bracket minus on the bracket RF over R1 multiplied V1 plus RF over R2 multiplied by V2 plus RF over R3 multiplied by V3. So this is our V out during inverting summing amplifier. So if let the value of R1, R2, R3 are the same, let's assume the value of R1 equal to R2 equal to R3. So our circuit, it becomes simplified. V out becomes minus RF over R. R1 is equal to R2, this becomes R, total R, you assign R. Then in the bracket V1 plus V2 plus V3. So V out becomes, when simplified again, the value of R1, R2, R3 are equal, that becomes R. So minus RF over R multiply V1 plus V2 plus V3, that becomes V out. So let's say again, if RF equal to R, our results becomes V out becomes minus of or negative signal, that because inverting type of summing amplifier, V1 plus V2 plus V3. So summing amplifier, that we can call it adder, means according to the analysis we can add V1 plus V2 plus V3 when if RF equal with R, that means unity inputs. So we get adder, or inputs becomes adding. So this we can call it summing amplifier. So as you see in this PowerPoint, that is I1 minus VS1 over RS1, VS2 again RS2, etc. So equal with the V out over RF. So when simplified, V out minus RF over RS1 multiplied by VS1 plus RF. So when you see this equation, if RS1 equal to RS2 equal to RSN, that becomes RS. V out becomes minus RF over RS multiplied with, on the bracket, VS1 plus VS2 plus VN, etc. So if RF feedback resistor equal to V source, that is unity gain, V out becomes negative signal in the bracket VS1 plus VS2 plus VN, etc. So this type of op-amp circuit we can call it summing amplifier or adder according to the circuit analysis. That is how they analyze the circuit of the op-amp. You can see adding of our inputs. Let's say example. Find the output voltage of the following summing amplifier circuit. If V1 2 millivolt and R1 becomes 1 kilo ohm, and V2 5 millivolt and R2 becomes 2 kilo ohm, our feedback resistor is 20 kilo ohm. Determine V out. So this circuit is inverting summing amplifier. So what is the gain of inverting summing amplifier? Minus feedback RF over R1 on the bracket V1 plus V2 plus V3 when both resistors are equal. But in this circuit it has different resistors, so we can use by using superposition theorem. Let V2 become 0, then doing this V1 only, and let's get V1 in the V out, or the gain of V1. So how they calculated, let's see. So our gain is V out over V in equal to minus RF over Rin. That is our inverting type of amplifier. So we can now substitute the value of resistor in the circuit as shown. So gain 1 for that V for V1, 10 kilo over 1 kilo, that becomes minus 10, the gain of for V1 input. Again, for the gain of V2, 10k over 2k, that becomes minus 5k. So how they do? First, let V2 become 0. That's analyze the traditional circuit superposition theorem. By doing that individually or separated, you can analyze, then we can add all outputs. So we know that the out voltage is the sum of the two amplifier input signal and is calculated as V out becomes gain of 1 multiplied by V1 plus gain of 2 multiplied by V2. So our gain 1 is minus 10, our input voltage is 2 millivolt plus gain 2 minus 5, our V 5 volts. So our output becomes 45 millivolts. So 2 millivolts plus 5 volts is 7. But that is our input and feedback resistor is different. So the summing output of this circuit becomes negative 45 millivolts. Let's see example 2. Find the output voltage of the following summing amplifier. Look, V1 3 volt, V2 1 volt, V3 8 volt. But the RS sources R1, R2, R3 are the same values, and the feedback resistor also the same values. So our gain is a unity. So the gain of for this inverting summing amplifier is unity, because 10 over 10, that is unity. So our result becomes summing of the input one. So such type of summing amplifier is called summing amplifier with unity gain. That means gain of RF over Rn is becomes 1. So what was the result? So please put the answer for this one in the comment box. Okay, so let's continue. Where they apply summing amplifier? Summing amplifier application is, so what we can use summing amplifier for, if the input resistance of summing amplifier are connected to potentiometers, the individual input signal can be mixed together by varying amounts. For example, measuring temperature, you could add a negative offset voltage to make the output voltage or display read 0 as a freezing point, or produce an audio mixer for adding or mixing together individual waveforms, that is sounds, from different source channels, vocals, instruments, etc., before sending them to combine it into an audio amplifier. So let's say example, according to this summing inverting amplifier, look at vocal, guitar, drums, all are to the inverting amplifier. So when you adding or sum of these instruments, 3 of them, that we can call it summing amplifier audio mixers. So one application of summing amplifier. Another type of application, digital to analog converter summing amplifier. Another useful application of summing amplifier is as a weighted sum digital to analog converter. If the input resistor Rin of the summing amplifier double in value of each input, for example 1k, 2k, 4k, and 8k, 16k, then digital logic voltage is a logic level 0 or logic level 1. On this input will produce an output which is weighted sum of the digital input. Consider the circuit as below. So this type of circuit we can call digital to analog converter. This is a summing amplifier application. So in the next you will see about differential amplifier, that means subtractor. When our op-amp have different input circuits, but we need to differentiate. So let's see how to analyze or the gain of these outputs. So during differential amplifier, to determine V out by applying KCL, I1 plus I2 equal to 0. So when you simplify this KCL to find out the V out, so let's see. So our inputs are two different voltages. One is V1 to the inverting signal, and the other V2 is to the non-inverting signal. So what about V out? How to get V out? So V out becomes, let the gain of for this differential amplifier by using a sim K, so V2 minus of V1. So according to the rule of op-amp circuit analysis, V non-inverting equal to V inverting. So our V non-inverting is a voltage divider through the plus signal, that is non-inverting signal. So V non-inverting becomes R2 over R1 plus R2 multiplied by V2. This is our V non-inverting input. So V non-inverting means R2 over R1 plus R2 multiplied by the whole of V2. So again, according KCL method or applying KCL, I in equal to IF. So let's simplify I in. When I in means V1 sort of R1 minus of V inverting. Again, IF from V inverting sort of R2, V inverting sort of R2 go to the minus of V out over R2 of the feedback resistor. So again, when you simplify this, V1 over R1 minus V inverting over R1 equal to V inverting over R2 minus V out over R2. So this means when you move this V inverting over R2, V1 over R1 minus of V inverting over R1 minus of V inverting over R2 equal to minus of V out over R2. Again, let's see, simplify this one, R1 minus V inverting the whole 1 over R1 minus 1 over R2 equal minus V out over R2. So this means V1 over R1 minus V inverting, when you simplify this one, R2 plus R1 over R1 multiplied by R2. This becomes minus V out over R2. So V inverting means, according to the virtual ground short circuit, V inverting equal to V non-inverting. So our V non-inverting, we get this value. So substitute the V inverting by non-inverting. So V1 over R1 minus, this means R2 over R1 plus R2 multiplied R2 plus R1 R1 R2 multiplied by V2. It becomes minus V out over R2. So R1 plus R2 cancel by this, R2 by R2 cancel it. So our result, V1 over R1 minus of V2 over R1, this becomes V out over R2. Again, to get V out for this one, V out means when simplified V out, V out means minus R2 over R1 V1 minus V2. This is our V out. Again, let's see this negative signal multiply for both of them. V out becomes R2 over R1 V2 minus V1. So this is our V out during differential circuit. This is V out during differential circuit. Let assume, or if R2 equal to R1, our result is V out becomes R2 R1 is equal to, that's unity. So V out becomes V2 minus V1 if R2 R1 are equal. So summing amplifier becomes analyzes by this one. So that is subtract, what we call it subtractor. So useful terms during differential amplifier: if both inputs change together, this is a common mode input change. If they change independently, this is a normal mode change. A good differential amplifier has high common mode rejection ratio, that we can call it CMMR. In the previous we have seen about common mode rejection ratio. So where they apply differential amplifier, very useful if you have two inputs are corrupted with the same noise. Subtract one from the other to remove noise. Remainder is signal. So main application example, an electrocardiogram measures the potential difference between two inputs. So this is one application of differential amplifier. Another instrumentation amplifier. Instrumentation amplifier are very high gain differential amplifier which have a high input impedance and a single-ended output. Instrumentation amplifier are mainly used to amplify very small differential signal from strain gauges, thermocouples, or current sensing device in motor control system. So another application of differential amplifier is instrumentation amplifier. Again, Wheatstone bridge differential amplifier is an application of differential amplifier. The standard differential amplifier circuit now becomes a differential voltage comparator by comparing one input voltage to the other. For example, by connecting one input to a fixed voltage reference set up on one leg of the resistive bridge network and the other to either a thermistor or light dependent resistor. The amplifier can be used to detect either low or high levels of temperature or light, as the output voltage become a linear function of changes in the active leg of the resistor. So from this R resistor, one of them is light dependent resistor. According to this input, our output also change, differentiate. Again, comparator also the application of differential amplifier. The comparator has many uses, but the most common is to compare the input voltage to a reference voltage and switch the output if the input voltage is above the reference voltage. If the goes more positive than the reference voltage set by the voltage divider, Vin greater than V reference, the output change state. When the input voltage drops below the preset reference voltage and Vin less than V reference, the output switch back by using negative feedback. The comparator can be converted into schematic trigger circuit. So this is our V reference. When you see in this circuit, R1, sort of R1 go to the inverting input terminal of the op-amp, and R2 also. So the V reference, according to the voltage divider, we can get VCC multiplied of R2 over R1 plus R2. So V out when V in greater than V reference, that is positive. When V out becomes less than V reference, that is a negative terminals. So consider the following non-inverting open loop comparator as shown below in the circuit diagram. The input applied is a sine wave of peak amplitude 6 volt. our input is 6 volt. The reference voltage is generated from potential divider as shown circuit diagram below. Look it, when it determines this V reference, that is VCC multiplied 3K, that is R2 over R1 plus R2. This becomes our V reference is 3 volt. So the reference voltage is 3 volt, then our input is 6 volt. So that means our V out, that is positive or negative, if Vin is greater than V reference, that is positive saturation. If Vn is less than V reference, our out becomes negative saturation. So like the operating circuit can be explained with following two conditions. When Vn greater than V, then V out becomes positive saturation. When Vn is greater than V reference, that is positive saturation. When Vn less than V reference, then V out becomes negative saturation. So our Vn is less than V reference, so R is negative.